Banked curves are a little different from other uniform circular motion. And you think of it's also different from inclined planes in a way. And the reason is when we broke down inclined planes, we broke it down so the frame of reference was one of the axes was in the direction of the acceleration, which was down the ramp. Well, in banked curves, the acceleration, it's not sliding down a ramp or up a ramp, right? The acceleration is towards the center of the arc that it's driving on. So it's actually going to be horizontal. So the free body diagram, well, if we have frictionless, and this is a very typical first thing to do, is we've got this banked curve, the car is going around, it's banked at some angle theta. We have the radius, and we want to find the angle for which a car can round a curve at 20 meters per second even without friction. Okay, so it's going at a certain speed. Obviously, if the road were flat and it were trying to round a curve and it's frictionless, it would slide out. So we bank the curve to kind of help to keep the car in the desired radius at the desired speed. So let's see what happens. If we do a free body diagram for a car on there, we'd have mg, and the contact force is from the road, and it's going to be the normal force. Again, it says without friction right now. It'll get harder. Now, frame of reference, again, the acceleration is a centripetal acceleration towards the center of the circle. So we have to define our frame of reference this way. So the normal force now will get broken down into components, and it gets broken down to n cosine theta and n sine theta. I will leave it to you to figure out the angles on that. The way I think of it is if the angle is very, very, very small, the normal force, the perpendicular force will be very, very, very big. So n cosine theta will be mostly up, and cosine ends up being bigger for small angles. So whichever way you do it, this is how it breaks down: n cosine theta, n sine theta. In the y direction, it's pretty straightforward. Sum of force equals ma. N cosine theta minus mg equals m times 0. It's not accelerating up or down. So we have the normal force now. Notice it's different from in the inclined plane situation. The inclined plane situation, it ended up being mg times cosine theta. So you've got to be aware when you're doing banked curves. It's a different frame of reference. In the x direction, n sine theta is going to be equal to mass times centripetal acceleration v squared over r. We can substitute our n, and we can solve for theta. So when you substitute the n, you end up with mg tangent of theta equals mv squared over r. The m's cancel. And that's very common. It's really important, meaning any car is going to be able to do this. The m doesn't matter. So that critical angle is 53.1 degrees. So that's very, very useful thing, because this is without friction. We're going to eventually have to do it with friction. In other words, it's not driving at the right speed for that angle. Okay, this is that problem. Car drives around a 25-meter radius curve banked at 15 degrees. What speed would be required to keep the car from sliding without friction? You always have to solve this first, because we don't know what direction friction is until we figure out whether that car is going too fast or too slow for that ideal, for that given angle. So first thing we're going to do on this slide is we're going to really repeat what we just did. There's our free body diagram. We're going to use that same frame of reference. Okay, so we're going to break n cosine theta and n sine theta. We solve it exactly the same way. Remember this, normal ends up being mg over cosine theta. And in the x direction, same thing, except now we're really trying to find the velocity instead of the theta. So once again, when we substitute n in there, mg over cosine theta times sine theta is mg tangent of theta. The m's cancel. Tangent of theta equals v squared over r. V squared equals tangent theta r. When we solve that, square root of that, we end up getting 8.1 meters per second for our critical speed. So that's how fast it goes without friction. A car can go on that curve. Now, let's talk about what happens when we have friction. We first have to establish the no friction velocity. And then if it's going slower than that, think if a car stopped on a frictionless ramp, it would slide down. So if it's going slower than the no friction velocity, it would slide down a frictionless incline, so friction has to be pushing up. Now, if it's going faster than the no friction velocity, it would slide off that way, would drift up the incline. So friction has to be pushing down the incline. Okay, so slower, I always think of it, the easy one to do is zero velocity. Zero velocity, that car is going to slide down the ramp. Friction must be acting up the ramp. If it's going faster than the critical velocity, well, clearly the friction would act down the ramp. Okay, so now we're going to do the second part of that problem. If the car travels at 5 meters per second, find mu static necessary to keep it from sliding. So we have the same free body diagram. We're going to break up the normal force the same way, but now we have force of friction. Again, it's going slower than the critical velocity, which was 8.1 meters per second. So friction has to act up the ramp. We break that down, and you find it breaks down this way. Force of friction times sine of theta is straight up. Force of friction times cosine theta is to the right. So that changes our equations and makes them more complicated. Vertically, n cosine theta plus force of friction times sine of theta minus mg equals the mass times 0. And then we substitute in mu static times normal force for the force of friction. So that's our first equation. Our second equation is also really pretty complicated now. N sine theta minus ff cosine theta equals mv squared over r. Now, I want you to, and I'll substitute in mu s times the normal force there. I want you to observe these two equations. The normal force, if we just look at the upward ones, n cosine theta, ff sine of theta. So I want you to recognize that pattern. Anytime you do a banked curve, those two trig functions are going to be different from each other. N cosine, f sine. And if we look horizontally, we have n sine and f cosine. Okay, so if you've got them the same, you've done something wrong when you're breaking up your angles. Another thing I'm going to point out is, remember how that critical velocity, we didn't need the mass canceled out. Well, even in this, the masses will cancel out ultimately. It's not obvious, but it will ultimately cancel out. So what I will generally do is just put 1 in for the mass. So I'll put 1 in when I'm trying to solve these two equations, two unknowns. I am not going to do the math on that. I will show you in the next slide. You can pause to follow. What I do is I take those two equations and I basically substitute in the numbers. Then I try to get it so one of the coefficients in the bottom equation is the same as one of the coefficients in the top equation. You'll see what I mean. I multiply it by a factor so I can simply add the equations to cancel out something. So here it is. I assumed mass was 1. I multiplied the second equation by 0.2679. So you can see that mu n term will now cancel out when I add the two equations. Then I solve for the normal force, substitute the normal force back in, and I can find my mu 0.16. Okay, now we've changed it so the car is traveling at 10 meters per second, faster than the critical velocity. So it would tend to drift up. In this case, friction has to act down. So we break up our friction, and you'll notice those two equations are very similar to the previous pages, but the signs have changed on the force of friction. And I will not bother going through the solution of that. It's just the setup that's the important thing.